Only I focused then on the idea that surface tension depends upon composition of an interface. If we talk about the energy of an interface, it's actually the surface tension integrated up over some area, right? That's the net energy of an interface. And if we have a uniform tension over the surface, it's just the surface tension times the area. And everything I talked about last time was about how gradients in that could create stresses or forces. And there's this other field percolating along for many years that talked about gradients in that. And that drives forces. And when I bothered to pay attention, because the field is beautiful and has been going on for some time, I thought, that is so clever. And it ends up being so rich and something you can really play with. So I'm going to talk today about problems that are driven by gradients in area of an interface. That's it. Okay. And what I'm going to talk about are particles. And so this is also one of those talks that this is both a lecture that I think I can give pedagogically, and I'm going to be including in it work that's ongoing in my research group right now. So this is not sort of the classical stuff like I did last time. This is stuff we're doing now. Okay? But what we're going to talk about is the problem of what if we took a particle that had some well-defined shape, and we place it so that it's spanning a fluid interface. And the particle is large compared to the interface. So we can define the interface having some surface tension. And that because this particle is there, and it has some boundary condition where liquid, vapor, and solid meet, that says you have to intersect the surface with some angle. And if that angle were 90 degrees, this lecture could end now. Right? Just the surface would stay flat and nothing fun would happen. But let's let it deviate from 90 degrees. Okay? Let's let it be, say, that the liquid likes to wet this particle a little bit. So it comes up at the end, and it has to find some location along the side. And this thing also has to obey mechanical equilibrium. Okay? And I'll go into what all that means. But basically what it means is that anywhere where surface tension pulls down, there has to be a counterbalancing where surface tension pulls up. Because this particle is sitting on the interface, and if surface tension pulled down and nothing pulled up, it would go under. Okay? So this particle's sitting there, and because of its boundary conditions, it's distorting the interface. That distortion has area. Multiply it by surface tension, it has energy. So this distortion is an energy field. Isn't that something? Okay, and when you have more than one particle on the surface, this guy's energy field interacts with this guy's energy field. And they feel each other and interact in a symbol. That's what I'm going to talk about. And so the ideas of working at particles and interfaces and working with spheres, very well established. And I'll allude a little bit to that in the literature. But the idea of having funky shape, so here just a right circular cylinder, which we chose because all pointers could be used as props. Which we chose because we could make them with very well-defined conditions. Another problem that's just emerging is what if we had patchy wetting? I'm not going to talk about patchy wetting, but you can imagine I could put a particle with patchy wetting in a surface and it will create undulation. So it works out that the distortions create very, very regular changes in area and create interactions which create very well-defined assemblies. So these are chains made by cylinders at a fluid interface. This is a rectangular lattice made by those cylinders. And this is what happens if you have ellipsoids. So this is from my friend Jan Vermaat's lab. And he's made uncharged ellipsoidal microparticles. They come together side to side and make very, very flexible chains. So I'm going to try to work our way toward understanding what's going on in this problem. And one of the nice things about this as a motivating example is as a first cut you would just say, these are rod-like particles. They must behave the same way. So details matter. Right. So before I start, I'm going to just acknowledge that whenever I say we did this, we means my former postdocs and students, my current postdocs, and I'm missing people here. For example, I'm doing work with Bob Lahamy, which should have been noted on this slide.
Is there some kind of applied reason why you'd want to use anisotropic particles?
Yeah, so when I get to my application slide, I'll go into that more. There's both applied reasons that it would be great to do very well-defined things at interface histology, and also there's the applied reason that most things that are made on Earth are not perfect spheres. But then being able to define, to study irregular shapes as opposed to very well-defined geometries. Okay. Oh yeah. So there's, to motivate, let's just start talking about spheres. Okay. And so if we had a spherical particle that has some well-defined contact angle. Here, this is a particle that was partially non-wet, for example. So the contact angle between, this would be liquid, vapor, and solid. This angle is greater than 90 degrees. And so that's just the contact angle this sphere wanted to obey. If it had zero weight, it would have found its equilibrium location in the interface up, greater than 90 degrees. Like that, to satisfy its contact angle. Yeah? And if it was heavy, it can't sit in the planar interface. What it did was it would bend down, maintaining that contact angle, and would have some weight. And that weight would be supported by surface tension times this perimeter. So there would be some vertical component that would be supporting that weight. Okay? And so because of weight, this particle is going to stretch the interface and make some distortion. And Scriven wrote this paper in 1971 where they had just set up understanding just areas of interfaces. And they placed two spheres or two cylinders with perfect wetting conditions on a surface. It distorted the interface and they said, look, there's an attraction. And they didn't really point to mechanism. In this paper, they didn't. They just did the numerics. It was back when they were just turning their attention to the idea that, look, numerics are a tool, attack the problem. Yes, really. So then, this guy, D.Y.C. Chen, who's actually a terrific colloidal scientist, jumped in and said, this is all about the area of the interface. We can do this with an analysis. The analysis was started by Nicholson. Nicholson had wanted to understand why bubbles migrate up menisci. Chan wanted to understand why did these particles interact. So let me go and tell you what Scriven saw. When this particle creates a distortion, and this particle creates a distortion, I'll jump to the full punchline. This guy has some slope that is in the surface. This one has some slope in the surface. When they overlap, the slope of the interface goes down. That's really all that's happening here. So if we think about an area of an interface, and a small slope limit, or some area here, that goes down, the area goes down. You drop the slope, you drop the area. You drop the area, you drop the energy. So these particles, the closer they came together, the lower the slope became, they had an attraction. Okay.
Sorry, but you change also the outside of this guy because it's heavier.
Right, so let's just right now, for the purpose of this discussion right now, let's just say this particle is sitting in otherwise planar surfaces, and you're right, the far field boundary condition has to be treated with care. So this was assuming that it was an unbounded surface and far from the particles, that could be neglected. In bounded systems, changes in curvature can be very interesting. And I will allude to curvature effects at the end of the talk. Okay? I will, but even the migration among menisci was attacked in this way. So the migration among menisci, so the other thing that people had seen was that if you have bubbles, say you pour coffee and you have bubbles, then it migrates up to the edges of the cup. And so Nicholson did an analysis that looked something like this. He said, the Young-Laplace equation, which is the equation that governs the shape of an interface. We talked about this last time. The mean curvature times the surface tension balances the pressure drop across an interface. Right? If we have a pressure drop, which is owing only to gravity, we can write this way. If we normalize everything with, say, the particle dimension, the length scales, I can write this as, in a small slope unit, the mean curvature is just a Laplacian. If I normalize everything, taking my characteristic length as the dimension of the particle, I'm going to get grad squared h is equal to, remember my favorite dimension of the slope? I don't know which one my favorite last time, but I mentioned it. Some number, which is how important was gravity compared to surface tension, times h. So that's this is an equation that governs the shape of the fluid interface. It can be found by actually just doing a minimization of the free energy associated with the interface for a curved surface. And if anyone's interested, I can throw the notes from my interfaces class that does that minimization into this folder. Does anyone want that? The derivation of the Young-Laplace equation, or is that familiar to you? Would you like it? I'll throw it. It's an argument for.
Or you can sign it for homework.
Exactly. There it is. I'll sign it for homework and give you the answer. I'm nicer than mine. Okay. So he said the Young-Laplace equation governs the shape of the interface. And here A is what I call the particle length scale, and he assumed that was small. If we solve this thing, we're going to get a Bessel function in cylindrical coordinates. And near the particle, for length small compared to the capillary length, we're going to be able to just approximate that as a logarithm. We're also going to be able to approximate this as just a Laplacian equal to 0. And so he said, look at the excess area of the interface. This is all suggested by Nicholson and then formalized by Chan. And this is just sketching the main point. If you look at the area of the liquid-vapor interface, we have this expression in a small slope group, which we can divide between being some reference area of our vector plus the excess area. And we just manipulate the grad h dot grad h, noting we can write it, that should have a dot. It's an equation editor problem, in this form. And so we get the energy associated with the particles. Suppose I have particle A and particle B. Or suppose I have particle A and an external meniscus, the same argument ends up holding. Then if I have two entities interacting in the surface, and I'm going to use a superposition idea, then if I look at the grad h dot grad h, I'll have terms that are grad HA dot grad HA, not interesting to me right now. Grad HB dot grad HB, that's not going to tell me about interactions. And then I'll have the cross term. And the cross term is about A talking to B. Right? So if I do that and play around with it, this can be rearranged. It can be rearranged so that we write the energy is the height of the particle, the particle times the force, the vertical force that's acting on it. And what's ending up happening is that the particle's moving in the vertical force exerted on the particle. This ends up just being that this particle is moving around in the potential energy gradient created by its neighbor. So they're sinking into the well created by the neighboring heavy particles. They're rising up the meniscus because of the bubbles, because they have a vertical force on the bubble pulling it up the meniscus. Or if they're heavy particles, they fall down the meniscus. So that was the upshot of what's happening with the problems where you have particles with finite weight.
It might be worth marking that the math problem is the same as two-dimensional electrostatics.
Yes, so there's beautiful invocations of analogies to electrostatics, and this would be single particles, the heavy particles, or people talk about them as capillary charges. Yeah, that will become more, so this was the story. This is the story of heavy particles. But what happens if you have no weight? And so that's what we're going to talk about today. So who cares about particles? And from now on, I'm going to talk about particles with no weight. I'm going to say nothing right now, except for a little bit about applications. Then we'll go into it. So the story about applications goes like this. Getting particles trapped at interfaces gives a means of making stabilized emulsions without having surfactants present. So this is one of those things, I don't know why it's named a Pickering emulsion, but was first apparently reported by Radenstedt. I imagine that fight's long over. I'm not sure why it's the Pickering emulsion is the name, but that's what they're called. We have renewed interest in them. We talk about colloidosomes. We talk about using particles to stabilize emulsions for drug carrying, for personal care products. It works out that textures depend very strongly on the presence of, say, an oil in a water phase and what's on the surface. And so, for example, Unilever is a grand supporter of this kind of research. There's this idea of particles being used to pack densely together on a surface to create a stable suspension or emulsion is now something that's been so well studied over the past decade. There's books dedicated to it. There's a book by Binks. There's a really very, very nice PCCP special edition in 2008 that summarizes a lot of recent research in the field. I don't know.
Physical chemistry, chemical physics.
There we go. Physical chemistry, chemical physics. I always said PCCP. So there's a body of knowledge out there of spherical particles, crowded surfaces, and stabilizing interfaces that's quite lovely. So I'm not going to go into it, but it exists. There's this interest in making particles come together in thin films. And so that, instead of having weight make the distortion, imagine I had a sphere, and its diameter is big compared to a liquid film in which it's entrained. And let's suppose it's partially wet. So the liquid rises up to make some contact angle. You see, this makes a distortion, this makes a distortion, and when they overlap, there would be an interaction. So that's the argument presented by Kralchevsky and collaborators for why particles come together in thin films to make nuclei for colloidal crystals. Now, there are actually counter-arguments out there that say that the capillary interactions in the thin films cannot always win over interactions with the solid surfaces, and that the reasons that people get nuclei of colloidal crystals, this is an argument being put forth by Darsh Wasson, whose name should be up there. I apologize that it's not. I don't know why it's not. It is, Wasson. Good. Argues. Wasson argues that instead of all that's happening is a particle comes to, for example, so Kralchevsky and collaborators pointed to capillary interactions for making nuclei. And this argument came up again in very beautiful papers from Chicago, where people were looking at evaporating drops that contained colloidal particles. And what they saw was that as the evaporating drop proceeded, that there was a collection of particles that accumulated near the three-phase contact line. So the ideas were that evaporation near the contact line is fast compared to elsewhere on the drop. That this drop is put down with some contact angle called an advancing contact angle, and it can't move until it reaches a receding contact angle. I apologize, it gets messy. And that while it's trapped, colloidal particles get washed to this three-phase contact line. That the presence of those particles pins the contact line, and so there's a continued outward efflux of particles toward that contact line. And at the end, one is left with a ring. And that ring is called a coffee ring. Okay? And so this phenomenon harkened back to the colloidal crystal studies that had been done by the Kralchevsky and Nagayama in the 1990s. And so they point to capillary interactions as being the cause of forming the nuclei. And what Wasson says is instead that what's happening is that they indeed, this is the top view of the drop, that the colloidal particles are being washed in the thin film. That the region between them remains sites of fast evaporation. And so the particles are just being washed into the open section. These are not sliding along by capillary interactions. So this is an ongoing discussion, even the formation of the nuclei and the role of capillary interactions. You have a question?
You mentioned that the evaporation flux is higher at the contact line. Is that just because it's being more highly curved than the rest of the droplet?
It's because we have a flux surface adjacent to a no flux surface. It's akin to the divergence in viscous stresses at 3 phase contact lines.
And the problem with the charge disk and electrostatics.
He will always supply the electrostatic analogy, which I'm very happy to have you do. Okay. So, so who cares about a colloidal crystal? Were we trying to commercialize coffee machines? And the answer there is no. It works out that in material science, the ability to make a colloidal crystal. So this is a colloidal crystal that was made in my group just so that we could have good pictures to put in talks like these. It's true. That we just made by evaporation. We evaporated a colloidal suspension. The particles were pulled together. As the suspension continues to evaporate, capillary interactions between the particles pull them into crystalline order. And there it is. For free, you've made a crystal. And now these crystals are being looked at for applications for interesting propagation of signals via photonics and other applications. There's also people who are using them as interesting templates where they want to make, say, a separation membrane with a certain porosity. They'll infill between those particles with some material, and then they'll get rid of the particles by some reaction technique. Often they melt them away or vaporize them away around some other temperature. Okay, so there's a lot of interest in forming organized assemblies. There's another field in which people have tried to place particles in a certain position on a device, a parking pad, where you dip coat a surface, and that surface has patches on it, which are well wet. So suppose this is wet, suppose this is wet, and in between things are non-wet. And we take that and we put it into a colloidal suspension and we pull it out. And then we pull out drop, drop. And if the drops are at the right height, you can place particles that tear off at the contact line into little parking spaces. Okay? And that's still ongoing work. For example, they have nice variants of that at IBM to try to understand how to make, in high throughput processes, interesting materials. And there, instead of also using wet patches, they use the ultimate wet patch. They make a groove, a pocket. Okay. But then the question comes, what if you're not a sphere? Well, first of all, and what if you have no weight? And that's what we're going to talk about. And there is some work in the literature on this. This is an evolving field. As with almost everything, you think you're the cleverest one in interfaces. Either Whitesides, Michael, or David have been there first. And in this case, it was Whitesides, unless Michael and David have work to tell me about it. So George Whitesides, years ago, thought about the idea of making complex shapes in interfaces. His shapes were not tiny. They were on the millimeter scale. But he was able to show that the ideas that came out of these particles interacting was that if these particles are both, say, heavy, they created a distortion that had the area go down when the distortions overlap. When the distortion from this guy overlapped with the distortion from that guy, the slope here went down. And so the area went down. And they called this a positive capillary charge because of that analogy to electrostatics. And they said, you know what? It's like electrostatics, except like charges attract. Okay? Make sense? So now let's do that same little superposition. So let's make this one light, and let's make this one heavy. When their distortions overlap, these should come back to the same reference plane, but when their distortions overlap, here, my slope goes up. So opposite charges repel. Okay? So Whitesides played with this game. He said, you know what, I don't want to just make little point particles. I'm going to make, say, a rectangle or a square. And I'll make this face partially wet, and this one partially non-wet. Positives will go to positives, negatives will go to negatives. I can make a lattice. They said, well, that was too easy. Now let me make a hexagon. and let me make certain faces that will come together with certain rules. And he made these very beautiful capillary puzzles that would sort of come together in very well organized structures. But those particles still had weight, and there was lovely work. So there's motivation. There's also work on rod-like particles, which I'll allude to today, and some really funny shapes, which I'll also allude to. Okay, so there it is. That was all motivation and warm-up. Now, we're back to this problem. I want to know this. If I put a particle with a funny shape in the interface, how will it interact? The last piece of background. A fight that was going on in the spheres interaction. Everything I'm going to talk about today, while I invoke analogies to electrostatics, I'm not going to talk about particles that are carrying charge. If they carry charge, there can also be electrostatic interactions, and I'm not going to discuss them today. But there was this discussion that was going on in the literature, where people said, so we'll go back to the Scriven and the Chan papers, there was sort of implicit in that was that if a sphere is creating a distortion only because it had weight, then if it had no weight, it wouldn't create a distortion. Right? So if I were in a limit where the weight of this particle was very small compared to surface tension forces, it wouldn't distort the interface. Then I would have this thing settle in to its contact angle, and it would sit in a planar surface. And then if it had some neighbor sitting at some distance far compared to the normal sort of colloidal interactions, so far enough that the normal interactions of van der Waals and things didn't apply, then this one wouldn't see this one and they wouldn't interact. And then there was a very, very nice paper in 2000 that said, well, first off, I should also tell you, in experiment, particles refuse to cooperate. If you put small particles at fluid interfaces, they played with each other. Okay? You told this one, here you are, you have nothing interesting, you have no interest in your neighbor, and he said, oh. Okay? So something was going on. All right? And so this debate went on as to what was going on, and there was a lively discussion about some electrostatic interactions going on in the literature at that time. And so people, but the discussion usually started saying, we can discard capillary interactions, so let's look over here. And Stanley's paper said, you know, let's not discard capillary interactions. He says, I will agree that if you take a sphere of negligible weight that has a perfectly smooth surface and a perfectly homogeneous surface energy, that we could place it in a surface and it would keep the surface completely planar. What if my sphere either had roughness, some roughness on its surface, some patchy wetting? What if my spheres were a little ugly? And what if I just relaxed that boundary condition? And just say, what if I don't say you always keep a uniform contact angle, but that you have some irregular meniscus? And that's the problem he attacked. So this is his sketch of an irregular meniscus. Okay? And this is what he said. He said, well, this is the Young-Laplace equation, right? The mean curvature times the surface tension is equal to the effects of gravity. He cast in dimensionless form. We're familiar with this. He got the bond number. He said, if weight is negligible, let's make that 0. It's negligible. And for microparticles, it's on the order of 10 to the minus 5, 10 to the minus 6. It's small. So he said, well, now we're left with a Laplacian. Okay. And the Laplacian admits a multipole solution. And so if I don't know what my contact line is a priori, these are the kinds of deformations that thing could excite. And he kept the decaying modes because he said far from the particle, and we assume the surface becomes plane. Then he went through this and he said, well, let's go a step at a time. This particle, so one thing that's clear is that if we did have a uniform contact angle, we could have a trivial solution. So the old answer is in there. It's just the trivial solution. We said, well, now let's go through the multiple expansion and go term by term through and see what is going to be the dominant contribution. And so he looked at the first term, which goes as A naught log R. That's the solution because of weight. Okay? And so that coefficient A naught would have in front of it something owing to the particle weight. So the idea is that if we integrated this around the particle say would have some body force to make a logarithmic distortion. And the force balance would give you A naught. Since we don't have a body force, the force balance gives us A naught is equal to 0. So the logarithm is not allowed to play. Then we look at the next term in the expansion, and it's a dipole. And it's saying my contact angle varies as cosine theta around the particle. So if I had my sphere, that would be saying my surface is high on one side and low on the other side. Okay? And surface tension would do this. It would make that rotate out, because that's a torque. Is that fair? So, monopole gone, dipole gone. The first survivor is the next term in this expansion. The reason that matters is that we just said for any arbitrary undulated meniscus, the first term in a decaying expansion is going to be this term. This is the long-range interaction. It's the long-range shape between any funky contact lines. Okay? And so I'm just going to go through it in tremendous detail. You guys kind of know about it. It's an analogy to electrostatic. It's a quadrupole. It's saying that if I were taking a top view of my sphere, that my deformation, the leading mode that could be created, I just put something ugly on that surface, and the leading mode would be rise at one pole, depression along the equator, rise, and depression. Okay? And that would be the kind of distortion that would be exciting. And it's called a quadrupole, and in the literature it's capillary quadrupole. So Stebe then went further. He said, let me calculate the excess area in the interface between two capillary quadruples. And he did that exercise, and he saw something very nice. He saw that it had an energy, and that energy was going to decrease as the particles approached. He also saw something about orientation. Let's suppose I call this the axis on which we're going to have capillary rise. Rise and rise, we're going to have fall and fall. That's sphere 1. Here's sphere 2. This little angular argument, phi1 plus phi2, that just meant that these things always want to come in mirror symmetry. They can come this way, they could come this way, they could come that way. It didn't select the angle. It just said they had to have equal and opposite angles. So here's a bunch of stuff in an interface. He was interested in spheres. I'm interested in shape. There's another problem that hasn't been attacked seriously today, which is, what if we make very controlled patchy webbing? Okay? But any undulated contact line, they've got to make a quadrupole, and those quadrupoles should interact. Okay. So here's a result that my postdoc Wenzaboto found in literature from Hinch, a floating Popty sphere. And you can see it's making a distortion with quadrupolar symmetry. Here is some work done in Arjun lab with J.C. Boudet, and it's an ellipsoidal microparticle, and you can see it's making a quadrupolar distortion. Here's a right circular cylinder, a top view of it in my lab, and you can see it's making a quadrupolar distortion. Okay. Over here are some bent spherical particles, and I didn't have a nice interferometer. These are flat, actually, these are not spherical. This is a really nice experiment in which they made little metal flakes that were circles, lithographically, in a thin film. And when they released them, they bent. And who here has ever seen a Pringles potato chip? They're not delicious, but they are nice to look at. Okay? And so these are Pringles potato chips, rather expensive ones, on the micro scale, assembling at a surface. So let me, before I go into, I want to talk about cylinders next, and before I go into blah, blah, blah more about cylinders, I want to show you why you're going to care. So I'm going to skip and then go back. So here's what, yeah.
Before you go on, I wanted to ask if anybody has ever been able to actually make non-interacting colloidal particles in nucleus. Or does this quadrupolar thing always happen?
I believe that there are open assemblies for highly repulsive spheres of interest, but I can't say that with confidence. It might be that it always happens. I truly can't say with confidence. Do you know of open structures made with spheres on surfaces? It might always be.
What if they were fully wetted?
What is that?
What if they were fully wetted?
If they're fully wetted, they're underwater. If they're fully non-wetted, they're up in the oil phase and they sit on top of the surface. So then that's cheating. If you say you're not allowed on the playground, we can't see if you can play on the swing set.
You actually can sometimes see them when you put colloids, latex colloids on an evaporating drop.
Yeah.
You see structure with a distance, an actual distance.
Good, so you can get an open repulsive structure. Good, thank you.
But that's using electrostatic.
So you can get an equilibrium distance. But there's also electrostatic interaction with surfaces that can be very uneven. Okay, so but here's why I care about shape. I motivated a little bit with the opening, but here's what happens with two cylindrical microparticles at a surface. So these two are starting out aligned end to end. These are microparticles that are about 10 microns long, maybe 20 microns long, 7 in diameter. They see each other. Okay, so there's weren't magnets, and actually my daughter, who's 10, once said to me, "That surface tension? I didn't know it was that interesting, Mama." So they approach and now these two are encountering each other side to side for the first time. Try to watch what they do. Always. Always. Okay, so cylinders chain end to end with high reliability, and we found that intriguing. So now I'm going to talk about cylinders and shape in more detail to try to understand why. So what's interesting here is I already showed you an image, and I'll go into more detail. We had a distortion that was quadrupolar, right? But instead of having just any old angle, and we always have mirror symmetry, but we always select so now you might have some patience in me talking about cylinders for a little while. So we made cylinders. And the cylinders we made by spin coating down an epoxy resin. And this is the same epoxy resin that is used everywhere to make microfluidics devices. It's the hard master that people make before they put the PDMS on top. It's the same glue, okay? And so we took this, and you illuminate the thin film with circular holes in a mask. And everything that's under the mask gets cross-linked, and everything that's not under the mask did not. Then you go through a couple of developing steps, and you can get these things like with little soldiers all standing in a row, microcylinder, 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 microcylinder. You can make them in high quantity with very well-defined control of the geometry. And it works out that these interactions, our bond number is order of 10 to the minus fifth at this scale. And the argument should just get better as we get smaller. These are convenient to look at under a microscope. And so if we sonicate these things gently, they come off of this lower layer, and we can just put them on the vapor. So that's how we got our particles. And so there are funny things that cylinders have to make you think about right away. A cylinder can satisfy its force balance at the interface by lying on its side. And we already know something about the distortion that's going to happen. We'll have some, if it's partially wet, we'll have some rise at the end, which pulls down. And there has to be some upward pulling along the sides that pulls up. And you can see already that makes it be a quadruple, right? Up and down. But it can also do this. This is a cylinder of negligible weight. And for things of negligible weight, so it can do this. Here's my cylinder. And if we have a corner, then the contact line will just hinge off that corner and do whatever it has to satisfy mechanical equilibrium. Okay? There's no such thing as a perfect corner. So there's lots of ways to think about that discussion. One way would be, what if we went zoomed into the corner and we had some finite radius of curvature there? That contact line could find its position. But that can even get messier, because what if you had include edges, etc. But the basic story is that if we have a corner, the contact line can hinge off and satisfy its force balance. This thing has negligible weight, so it's not pulling down. So surface tension doesn't have to pull up. It sits in a planar surface. That's mechanical equilibrium. So we have two orientations for mechanical equilibrium. And the one that wins is the one with the lower energy. And the relevant energies left in this system are the energies associated with the surfaces. There's the energy of the liquid vapor surface, the solid liquid surface, and the solid vapor surface. So you just add them up for each configuration. Whoever's lowers win. If you equate them, you can find the coexistence state. And this is just a coexistence curve between the two. So the upshot of that is that short particles want to sit end on. Longer particles want to lie down on their side. So you can understand that by doing the analysis in detail. And then you could ask yourself, why is side-on favored for longer particles? What's driving all of this? So this comes back to your question, which was, what if it loves the liquid? The only reason a particle is at a surface is if making a hole in the interface lowers the energy of the system. That's why it's there. And so as a first cut through these data, you could say the orientation that makes the bigger hole in the interface wins. So standing up, the biggest hole you can make is pi r squared. That's the hole you make in the interface. Lying down, the longer you get, the bigger the hole is in the interface. Right? So if I make it longer and longer, and I can approximate that hole in the interface as a first pass as just a rectangle that cuts through my cylinder. If my cylinder really was indifferent between liquid and vapor, I'd have a contact angle of 90 degrees, and that rectangle would be LD, right? But if I'm partially wet, I'd be underwater more, right? I'd make a thinner rectangle. And so I've got to weight that rectangle with my contact angle. So if I equate those two, I can get a prediction for coexistence, which is embarrassingly simple. It says that my aspect ratio with some weighting constants goes as 1 over sine theta. And that does a half-decent job of capturing the data. I think that's this dashed curve. And from now on, all that we're going to talk about is particles that are lying down. We've made them sit up, if they're small disks, and you make them long enough, they will. Okay, so now, we know that they can assume two different orientations, and now we also know that they chain. So they did things that agreed with Stebe. They interacted, and they did things that disagreed. They selected negative. So to understand the shape around those particles more, we look in greater detail. And so if you look around the particles, this is a surface evolver simulation. Do you guys know about surface evolver? It's an open source code by Brack, which one can use to find the minimal free energy configuration of a surface. And it's a very lovely piece of software. So the idea is that there are many, many different locations of the contact line that could have satisfied mechanical equilibrium, but we had to find the one with the lowest energy. So we did it numerically. And so this is the wetting configuration. And far away from the particle, it becomes a quadrupole that one could describe in polar coordinates or cylindrical coordinates. But closer in, there are important distortions that are happening. We see the rise at the end is about 3 times higher than the fall of the sun. Okay, so somehow the rise is being concentrated at the end here. But then we want to say, well, if this is numerical prediction, how does it compare to experiment? And it does okay. This is a particle trapped in jello.
So, last lecture you showed us all these wonderful examples of how surfactants can act to inhomogeneously play with surface tensions. What happens when you have surfactants in these types of systems?
Yeah, this is a beautiful question. So there are 2 pieces to the answer. First of all, let's look at it from the particle point of view. If we put this particle in the surface, I wanted the particle to control the distortions that were made in the interface. So we're making some well-defined geometry for the particle, which is making some well-defined distortion, which is making some well-defined energy field, which is a signature of that distortion. If we put surfactants in the system, and they adsorb non-uniformly on that particle, they can create patchy wetting. And we'll always have a quadrupolar interaction. But the near field things that were the signatures that made these things know, we're cylinders, we like to come end to end, those could get messed up by patchy wetting. Okay. But the interactions would still occur, but now they would not just be signatures of shape, they'd be signatures of shape plus patchy wetting. Now there's another very nice question, which is, can the presence of surfactants make it difficult for this particle to migrate toward this particle? And the answer is yes. And that's not very well studied. I'll show you some data which were sort of an extreme case, where we could make them just locked in a frozen surface. Okay? But the in-between cases of, can we create gradients around these particles that are opposing their motion? Yes, they should be there. But they haven't been documented in any systematic way of sort of like the hydrodynamics I was showing last time. Okay. So we have a distortion field, please.
You ever tried doing this between different fluids, different types of interfaces between different fluids that don't mix?
Yeah, I'll show you some. So all I need is an interface with a surface tension. So it can be surface tension, the interfacial tension can be liquid vapor, liquid oil, water oil, etc. If you want to go to complex fluids that are polymeric and elastic, you might get some very interesting competitions having fun. Okay. But so we have our distortion. We have pretty pictures of our distortion from the numerics. We have pretty pictures of our distortion by putting our particles in jello. So it's not called jello. Do you guys know what jello is? Is that ubiquitous in the world? Sticky, sweet stuff that starts out warm and liquid, and then you put it in the refrigerator and it cools. Okay. So now take out the food coloring. And this is a sugar called gelatin that you can make nice and warm and place your particle in it and then cool it down. And you can place that system under an environmental SEM and get images. And that's what this is. This is a very expensive jello experiment.
Should we anticipate that the gelation reaction will relax out whatever stresses are present in the fluid state?
Those are beautiful questions. So it works out that there was some work done by someone named Panov, who wanted to understand the contact angles on spherical particles as they got smaller and smaller. And he calibrated the hell out of the system. Okay, so he did hanging drop experiments, bended drop experiments, and he made jello drops. Wouldn't that be a fun lab, right? And they still obeyed the Laplace equation. And he did all of these calibrations that suggested this was an okay visualization. But the student who helped do this work was done by Alice Sang, but the PhD student Eric Lewandowski hated stuff like this. He said, Kate, this is eye candy, it's not quantitative, don't present it. And I said, it's eye candy, and I will present it, okay? But it is eye candy, because this thing was put in environmental SEM, and there's evaporation sucking the liquid out of this gel as we're taking the measurement. Okay? So, they're pretty, and they're suggestive, but are they quantitative? But let me first tell you about the other pretty piece. You see this bell of depression? This nice curved blue region? Look at this curved region of depression. Done with eye candy. So quantitative. They set up an interferometer. I'm lucky enough to be in a department with John Clougher and have a postdoc with Larry Garvin. Both of you are just, if it's an optical tool, I swear they can go hit check a table and everything falls into alignment. Okay. And they set up this interferometer. And so if we take a cut, this is a top view of the distortions. This is an iso-height contour. Those little blobs are regions of rise. These are regions of fall. And this is where the height was 0 compared to the reference surface far away. This is a top view of the quadrupolar distortion in experiment. If we do a cut along this axis, along the rise axis, we have nice agreement. If we do a cut along the fall axis, we have nice agreement. And this is because of a coherent laser beam interacting with itself. It's not a cathode. So now we have something quantitative that says, okay, you understand the distortion. So things that agreed with Stebe. These particles were coming together, and far away, when they're at large enough separation, all they're seeing is the part where they think that they have a cylindrical polar particle, right? Something we can just find as cosine 2 theta in an r theta coordinate system, right? So far away, all they should do is what Stebe told them to do. And what Stebe told them to do was that there would be some interaction force that we had from his calculation. And his energy went as 1 over the separation distance to the 4th. So his force goes as 1 over the separation distance to the 5th. Take it as you are. Okay? And that interaction force is being balanced by viscous drag at every separation. And that balance is going to be some prefactor times the velocity with which they approach each other. And so we can equate this power of the interacting force to the drag force and predict a power law. That the change in the distance between the particles should go as a power law with some factor. Okay. So that was first done by J.C. Boudet, to my knowledge, looking at ellipsoidal microparticles and surfaces. And his ellipsoidal microparticles obey Stebe over a certain range of interaction. And our cylinders are also well behaved. When they're far enough apart, they come together with a power law in agreement with that outer fluid prediction. We can go a little further. We can say, oh, if interaction force is being balanced by viscous drag, can we integrate along that trajectory and find out how much energy was lost to viscous dissipation? And if we do that, we can find out how much energy is in this interaction. So we do that. We integrate up to find the drag. And it's absurdly large. I mean, it's actually correct. It's absurdly large. It's 10 to the 5th kT. These particles are storing a lot of energy in that deformation. And when we first looked at that, we thought, that is a goofy number. 10 to the 5th kT from a microparticle in a surface. And the answer is yes. If you look at this is an air-water interface, we always talk about that as 72 millinewton per meter. That's 18 kT per nanometer squared. So any interaction that gets rid of a little bit of area gets rid of a lot of energy. So we have a prediction which agrees to within prefactor with that dissipation, and I'll talk about that prediction. So now we know we have distortions interacting. When they're far apart, they obey Stebe. But Stebe told them, mirror symmetry, but any old angle will do. But our cylinders, yes. Okay, I'm going to deepen the intrigue. Ellipsoidal microparticles like to come side to side. So much disobedience. Stebe said, take any angle. We've got kissing cylinders. And I don't even want to talk about the ellipsoidal microparticles. I don't know what they're up to. Okay? But there's an attraction and a preferred orientation for these two different sets of rod-like particles that differ significantly.
So the difference, I guess, between the cylinder and the ellipsoids is the sharp corners, right?
Mm-hmm.
And,
Exactly.
okay.
You're right. And that's what I'm going to talk about. And that they just impose a massive barrier. But first of all, everybody has a preference. They've selected an angle. Stebe's analysis couldn't select the angle. So let's see why are angles selected. Then we'll talk about corners. But you're terrific. Look. Okay. All right, so go back to the distortion. And the top one, I used the pointer, but I'm incompetent. Here we go. The top one is the numerics. Okay? And Lorenzo Boto, who's working in my group, in his first week or so in the group, got this far and he said, it's an elliptical quadrupole. And I said, how do you know? And he said, intuition. I said, could you substantiate that? He said, of course. And he was right. Okay, so here's the idea, that if we take an ellipse and circumscribe the cylinder, so that's the right aspect ratio, that we can get a distortion then within 2 to 3 radii of contact of this particle, matches it. And if the agreement gets like within 90% near contact, and it gets better and better further away. And that distortion is a quadrupolar distortion, but now in elliptical coordinates. And all elliptical coordinates are is that they have reference surfaces in ellipses. That's one coordinate, and the other is hyperbola. Okay, so it's just another coordinate system. And it's a coordinate system designed to look at things that are elongated. And one big feature of our cylinder is it's longer. Right? What's even funnier is, let's suppose we went to one that had diameter and length the same. The circumscribing ellipsoid would still be longer. That thing would think it's long. So this is nice if you like to do calculus, because now we have a closed form expression for the distortion that we can find the excess area. Okay? But it's going to work for a while, and then it's not going to work. Because closer into that particle, we don't look anything like a quadrupolar. This is a map of excess area in the region of the corner. And there's a lot of excess area on that end face, and a lot in the region of the corner that are not going to be captured by saying, oh, I know the most important one. And in there, we're just going to have to just suck it up and do the numerics. Okay, so we did that. We calculated the excess area associated with the interface. So we have an energy field, and the energy depends upon orientation and distance. And there's a closed form expression which I'm going to spare you. But here we take that expression and we use it just in the explicit Euler scheme to update the position of the particle. And what we need to add to that is a drag coefficient. We need one for translation and one for rotation, and we pull them out of experiment. But so the top view is simulation, and the bottom one is those kissing cylinders that we saw earlier, right? That start out side to side and become end to end. And strictly speaking, we should stop the simulation at like 3 radii before contact. But it does a decent job of capturing this idea. Here's a preferred angle. And that preferred angle is tip to tip until the circumscribing ellipsoids are in contact. And so you go 1. And then you look further. And it says, but you know what? At closer distances, this is preferred. And we could actually think about that right away, right? This has rise, and this has fall. If we make rise overlap with rise, slopes go down. If we make fall overlaps with fall, slopes go down. Just imagine if you could lie next to each other. Rise overlapping with rise, fall overlapping with fall. Rise overlapping with rise. You get rid of a lot of area. Okay, so we won if I stop the lecture here. But then the same analysis as goes side to side. So the near field interaction are telling the cylinders to be different from the ellipsoids.
Sorry. Did you do anything with one fat cylinder and one long cylinder?
Mm-hmm.
So the ones that are actually short. So if you have one of the long ones and one of the short ones, what's going to happen? Because I'm just assuming the fat one, you don't have that gradient around it.
This is all gorgeous. And you guys you're anticipate the best parts. And so the answer is, yeah, we've done little ones and big ones. But instead what I'm going to talk about is what happens to a particle. I hope to close out with this. What if I have a particle that's sitting in a distortion field that's created by something much larger than it is?
Okay.
So that would be your little particle. And what the big particle was massive, big. Instead of making it big, I'm going to pin the surface in certain ways. And you'll see what a particle does locally when it's seeing some distortion. Okay? All right. So here's from Jan Vermont's lab, his uncharged ellipsoids. Here's the work that pioneered it by J.C. Boudet, the uncharged ellipsoids coming side to side. If they're charged, things change. I'm not going to talk about it. Okay? The reason is I don't have all the answers. You just have to know it's different. Repulsion matters. But repulsion is really ugly because it can also, under certain circumstances, change the surface distortion. Okay, so everybody's coupled. I only like problems where everybody's coupled. Okay, so right now we're throwing out charge. Okay? All right, so ellipsoids come side to side, the elliptical quadrupoles say come side to side. There was a very nice numerical analysis done by Lele where he compared tip to tip for ellipsoids and side to side for ellipsoids. That says come side to side. Everybody says come side to side. And cylinders go, I won't do it. Okay, so we have to look at the near field interactions. So looking at the near field interactions, we came thinking correctly that the corner mattered. We also came thinking that the area of this liquid bridge that forms between two cylinders must be the storm. So I'll change props so I can have two cylinders. We have two cylinders, they're coming together end to end. This is partially wet, this is partially wet, they make a liquid bridge between them. And we thought, boy, when you distort that, you must stretch that liquid vapor interface. That was partly true. It's not what ends up being dominant. So first point. Let's talk about rotating that end to end to side. That's what we're going to do a simulation. Take this, okay? So you're looking top down at the surface, and we want to say what happens when you do that. Okay? If I'm an ellipsoid, here I have a nice circular tip, and I can rotate while maintaining contact one next to the other. If I'm a cylinder, I have to hinge. Okay? And that hinging, that steric constraint, ends up being important. So what happens? So as you, here for just tiny angles, just looking at what happens in detail, and focusing on this end face. Say, just bend it a little, and ask it what happened. Okay? So we bend that a little, and we ask it what happened. And you know what it did? It slid its contact angle along. So here, it's contact line. Its contact line, the alignment was given here by the orange one. And as you rotate it, it slides down. And that change, so here we've assumed an equilibrium contact angle. Even drawing out what this could also, there's tremendous contact angle hysteresis that can happen in systems. This was not addressed. But if we say just you maintain your equilibrium contact angle, and what happens to the surface? It redistributes and moves the contact line. And that does something that this thing didn't want to do. Up here was solid surface, the solid end face, and here we're looking at this contact line for example. As we slid down, we exposed more solid surface. So the energy, so first the punchline is, that bending, this is aligned end to end, this is coming side to side. End to end has lower energy for cylinders, and there's an energy barrier to rotation, and this would be a metastatic state. Side to side. So if you came side to side, you might stay. There's an energy barrier to go around. But if you came end to end, that would be preferred. Also remember, these differences in energies are on the order of thousands and tens of thousands of kT. So my energy barrier is massive. Okay, so the different components of that. This is the most important piece of the energy, the liquid solid. The liquid vapor actually liked it when we went side to side. So usually when we talk about capillary interactions, I motivated the whole thing. That things come together because they lower the slope of the interface. And these guys go, we like to go the way we like to go because we want a certain contact angle, and we didn't really want to expose a lot of solid to the world, thank you very much.
Shouldn't that energy be highly singular around phi equals 0? Because like David was showing us yesterday with the structured posts, there's when you have a sharp corner and a contact line has to go around it.
This is, each one of these has their equilibrium wetting configuration where the contact line is already, we always have our corner. We didn't get rid of it anyway, right? I have a wetting contact line around here, a wetting contact line right here, and all I did, let's make this the plane of the interface.
So there's still some separation in other words. They're not touching.
We actually, these interactions, only accounting for the capillary attraction, there's no equilibrium distance between these cylinders. So we've artificially given them some small separation. Okay? In fact, there would be potentially some near-field repulsion that could keep them apart when they come close enough. So, but to do that in experiment right now, we're going to other tricks because the attractions are so big. We have to come up with tricky repulsions that are also big. Okay, so in contrast, ellipsoids slide down. This is the total interaction, also dominated by liquid-solid energy. So the liquid vapor energy discussion told them to come side to side, but the liquid solid energy told them really come side to side. The near field discussion. So now the question is, who cares? Do you care?
No, but I So with the cylinders, you know, worried about what's happening in between.
Yes,
If I put some soft material
yes.
and bend it, and can I ask myself the question, is the liquid capable of taking it down? Soft enough so that the bending energy is not that important?
You're thinking of taking the pair of cylinders and treating them as a single entity of soft matter?
No, I want something like a thread, just a single cylinder, and I'm bending so that I don't have anything in between the two cylinders. So I'm asking, is a straight object preferred to a curved shape or a man? So as to eliminate what's happening.
Yeah, that's a very nice question.
You need a long
And-
cylinder?
Yeah.
So what we did not do that. We were strictly interested in near field capillary interactions. So since we were interested in that question, we focused on that question. His question is, what if I took an entity, like what if my cylinders were rigid, they didn't have a choice but to stay rigid. But what if I say, think about my chain, and now approximate it as one great big long cylinder. Would the thing ever want to bend?
Wouldn't it depend on the size of the cylinder to the elastic
There
capillary
should be a
link?
critical
Yeah.
point where
Yeah, yeah. But I didn't play that game. I think there are nice games to play there, in particular if we then gave them back their bonds, and we get the bond certain strength. So one question would be, when will my chain start to bend? And I think that one could make analogies to polymers that would be very interesting. Sort of rotation lengths, chain interaction, and strength. So, but if we go back to the calculation for the energy, and we say, let's take the derivative of this energy with respect to this angle. That's going to be something that we're going to be relating to what torque do I have to put on this bond to bend it? And it comes out to look like this. The steepest slope is at the beginning. So if you think about trying to bend these things, you go, apply torque. Nothing, 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 static. Right? Nothing, 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 yield. So we know that these cylinders have stayed pretty rigid. And we've seen them in experiment. That's just the thing floating on the interface. It assembled and it just sits like that. But there are two experiments that we've done that suggest these things are rigid. So one of them is a surfactant experiment. And it's kind of a funny surfactant experiment. What we did was we took an insoluble surfactant, pentadecanoic acid, of interest only because it's so thoroughly studied there's nothing else to know. Okay? It's just a great reference insoluble monolayer. If we put it on an aqueous layer that is acidified, that thing is trapped at the liquid vapor interface. So we injected it at the liquid vapor interface, and we compressed it. And you can compress that thing, and it will be in expanded regions. This is the surface tension reduction of the surface pressure versus the area of the molecule. In the expanded region, it's in a gaseous state. Then it will go through a two-phase coexistence and go up into a liquid state. Then it will go through two-phase coexistence and go into another state. And still, we weren't satisfied. We compressed further, and it goes into another state. And then we compressed further. It started to pop out of the, make little crystals. Okay? We have squeezed the heck out of this monolayer. This is rather an extreme situation for a surfactant layer. And then we did that, squeezing with some particles in the surface. And the poor things were just sitting there going, how are we supposed to interact like this? You put us in a polar ice cap, right? They're in some solid thing. They can't find their neighbors. They can't move. They're stuck. Okay? And then we put base in the subphase. And the surfactant starts melting into the solution. And these things become free. So it was just a way for us to stop them, then melt it away and look at them and see what they do. So in this case, this is what happened. Is this the good one? Yes, so they just got the surfactants melting away, and they collect their neighbors. And they rotate, stick little chains, and they find their neighbors. Now the kink might be a funny cylinder, or it might be something screwy, but we can't. Like this last piece. Even off camera, it does something interesting too. So that thing, do you see they all collect to each other and shh. So they were nice and rigid. Okay. But that was a messy experiment.
Can you show
So,
it again?
oh, absolutely.
I was expecting to.
all right. So there they were trapped in that interface, squeezed surfactants all around, them, squeezed into a solid layer. Then we add base, the surfactant melts away, and they play. So there's a couple important points here. Look at this, they always had room to sweep around and find the other guy's end. If we do these sorts of experiments on a more crowded surface where they don't have room, you can get chains to come together side to side. Right? But these guys had room, so they just swept around until they found the end of their neighbor.
There is strong convection though. Is that what we see, the big movement of the...
So there's too much going on in this experiment to do anything quantitative, right? I've got a surfactant melting away potentially non-uniformly on the surface, and so we've got that convection, we've got these things sweeping around, finding their neighbors. That was just, in fact, that experiment was done years before we had the prediction that these things should be rigid. And then we're like, go back to the surfactant experiment, look what we saw. But now moving forward, this is work that's still in progress with my friend Bob Lahaney. What we're doing is we're integrating magnets into the chain. So all I need for a cylinder to join is that it have a similar contact angle. It will join the chain. So I can make it of an arbitrary material. I could make them out of anything. Okay? And here, this one, it's not a perfect match, but it's a little magnet. Okay? And he's just integrated into this chain. And this is being put under a rotating magnetic field, and this is what it does. Okay? So this is the end guy is feeling a torque of something like 10 to the third kT. He needs 10 to the fifth to snap, and since we didn't get there yet, he doesn't snap. So that's part of the story. That's the part of the story that was about rod-like particles. So there's actually rod-like particles that people care about a lot who are doing experiments with gold nanorods. They're really interested in spherocylinders. And those are the most boring case for capillary interactions, right? Because those things, if we don't have roughness or patchy wetting, are going to do nothing. A spherocylinder that has a uniform contact angle is nothing but, right? It's going to be able to sit in a planar interface. So we'd have to be back in STAMU land with weak distortions, only now these weak distortions would be weak distortions on a nanoscopic entity. Okay. So unfortunately, that's a reference case that's not fun, right? But the ellipsoids were really flexible chains. The cylinders made really rigid chains. These were guys that were formed in an interface where they didn't have room to sweep around and find the end. We squeezed a bunch of cylinders together, and they formed that sort of bamboo-like structure. And here, this was actually a very lovely experiment. We just took an oil and water suspension, shook it up, and we made this little lattice on the surface. And that's very lovely because you see that everybody's end-to-end and side-to-side are all in register. Okay. But these are kinetically trapped structures. My interactions are 10 to the 5th kT. I can't anneal them. So we're working on two different things. Going down in length scale. These interactions scale with radius squared. So if we go down several orders of magnitude in length, maybe we can get an annealable structure. And clever tricks to give repulsion. Those are the two things we're trying to do. So I want to say, I'll say one word about this, and then I want to show something about migration in a big distortion field. So there was a paper that was like a smart guy paper that preceded a lot of the work on funny surfaces, funny particles. And it was a paper that physicists would love. It's done by someone named Mukausen, who had usually done a lot of work on surfactant monomers. And he looked at that idea that was going around in the literature. This is a 1992 paper. He said, people say that if you have particles of negligible weight, they wouldn't interact with the surface. That doesn't seem right to me. And he focused immediately on thinking about near-field interactions. And he said, let's suppose I approximate my particles as two walls. This is such a lovely paper. It just can be done with a pencil. And he said, let's suppose on this wall, I have, in between the two walls, I have a liquid vapor interface. And on this wall, I scribe a contact angle. Let's call it a Fourier mode in Cartesian coordinates. Right? So sine k. And on this mode, let's scribe a contact. And let's ask ourselves, how does the area of the interface change when I do this? He already knew that if you squeeze things together, pluses aligned with plus, minus aligned with minus, you would get traction. But he asked about this. He said the energy is minimal when the distortion has the same wave number, the same frequency, the same amplitude, and is in phase. For that case, these things pull into an alignment. And he said, in principle, one could expect then that particles would assemble in registry and that they would be able to recognize each other. Okay. So we tried making some funny particles. Okay, but this is the early days of this idea. We're working on developing it more. Right? So here's what we did. We made two sets of funny particles. The first, to the top view, imagine I took my cylindrical particles, that mass, and I put a bridge between the circles. So when I cross-link that, I'm going to make little binoculars. Can you guys imagine that? Microscale binoculars of an opaque epoxy resin. Okay. So they have no interest for anything except making a distortion, right? So we take our little binoculars and place them on the interface. And this is the top view of the binocular, right? And it's making some distortion. And we let them come together. And then we made trinoculars, even more useful, epoxy trinoculars in the line. Okay. So here you see they interact. Far away, they just think that they're polar particles. And the trinoculars are the same sort of thing. And so we can assemble things with their sub-features in registry. We sort of did that with the cylinder anyway, right? The cylinder came together end to end. So one question would be, what if I mix that with that? Because the Calcin says they should self-sort. And you know what mine do? You've got binoculars, maybe trinoculars. It is an ugly scene. Okay? Because they can have local minima, which get them kinetically trapped. These things have to be smaller, or we have to invoke some repulsion. So what we could do, and what we're working on now, is we can have an undulation that's attractive and superposing that a smaller undulation, which is repulsive, that might allow this one to be repelled from that one going from. So I'll close with this discussion. What happens if I place these particles on a distortion that's big compared? So actually, it's a beautiful question. If you go back to the interactions that we've been talking about, the way we did the math, a la Stebe, is that we said, use superposition, okay, and look at how this particle moves because of the distortion field created by that particle. And it works out that what you do is you say, let's take a Taylor series expansion of this guy's distortion around here. And when you're done with that, what you get is an energy that says, this particle moves in a curvature field created by its neighbor. And you say, why does the curvature field have to be created by its neighbor? Why can't the curvature field be created by anything? Let's make curvature fields. Okay? And so there's some, Stebe alludes to this idea, and there's also some echoes in the literature in a couple of places. In previous work, we had shown that if a particle sits on a curved surface, let's suppose this is sitting on a surface that's saddle-like. Okay, so I have a surface that's going like that and like that. My particle wants to align its saddle with its host. If it does it, then the rise is overlapping the rise, and the fall is overlapping the fall. So you know what else they want to do? They want to migrate along to try to match this saddle to its host saddle. So let's suppose I create a surface, and I make a great big tall post. I pin a liquid interface here and let it fall away the distance from the surface, from that pinning site. So I have a tall micropulse, a liquid vapor interface, and the surface is falling away from that. Then this is a surface which has zero mean curvature. Far away, it's planar. Close up, it's characterized by the radius of the post. It looks like a saddle everywhere. If I place this particle on it, it thinks it's on the saddle. And this particle wants to migrate to match its saddle to its host saddle. So let's see that happen. So first, This guy is settling, so let me go over some more. This is the top view of my micropost. Underneath it, so draping from here and away was that liquid vapor interface. And we placed an oil layer on top, and we're placing little cylindrical bombs in the oil, right? So they're coming in, and then they attach to the interface. And then they're going to do something. So this is a top view of it settling in the oil. Gravity matters until it's attached, and then up, it aligned. You want to see that again? Settle, 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 align. And then, in this curvature field,
What's happening in the upper left?
I have an interface. I have here a tall micropost. It's 300 microns high. Okay? I have an interface that's pinned here and is draping away. This is water. On top, we have oil. In here, you place the microparticle. It's settled, because gravity matters till it attaches. Then once it attaches, that guy happened to attach with this way. This way on this axis. But what it wants to do is align so that it lines up the saddle shape it makes with the saddle of its host. So it attaches and goes, okay? And then it wants to do even more. It wants to ride the pony. Slides up the curvature gradient toward the post. So this is against gravity. This is exactly not what has been seen by previous migrations owing to curvature. Right? It used to be go down by your weight like a bead on a string. It's just getting right up. So it's rich. One can play with it a lot. And I'll show you one of my favorite things that we did to play with it. We make corners. So this is all work in progress, and I promise to give it to anybody at the end of the summer, but if I post it online, my students and postdocs will come. So, please write to me if you want the results. Look at these things. So you can migrate to the corner. So the corners are sites where curvatures diverge. Have you seen the particles that come in? And they form assemblies at the corners of the micropost, according to the curvature gradients. And those curvature gradients are beautifully complex. Because you see this region here that always remains naked? At first you say, oh, well, it's because the corner was attractive. But it works out that this planar site is a site of zero curvature. And far away, we think we're a monopole. So our curvature goes up and then down. This, the curvature gradient, points away from the surface. We have a curvature gradient repulsion from the solid boundary. And so here you can see the particle lands here and scoots to that corner. Let's watch the movie of this guy landing and scooting. And there I'll stop and take any remaining questions. Did you see? I'm sorry it blanks out at the end. Okay, we show it one more time, and then I'll conclude. So, I don't know if you can stop it from right now. Repel, snap.
Okay, so there's no other questions to usually know.
You some pictures where you have this rods line or forming layers, and I was wondering, it reminds me of liquid crystals, of course, and of synectic and nematic order. Do you think it could be possible to define the parameter order? And
All this is work in progress. I joined Penn 3 years ago, and liquid crystalline heaven. Okay, and this is something that we're working on. I wanted to show this also. J.C. Goudet sent me this. Apparently, bugs were onto it long before we thought of curvature migration. So this is from YouTube, and it's a bug. Can you guys see this little thing? Here's a bug who wants to ride up a meniscus. You ready? So this is not my result. We don't have a buggy left. Quadrupole, take a ride.
Surfing up the hill.
Isn't that great? Let's go surfing. Yes, so all those ideas, looking at this thing as a liquid crystal, giving it an order parameter, doing that as a function of scale. If we can scale it down, can we actually get different ordered annealable structures? Can we look at the one is a nematic, the other is a squaratic? Those are questions that we're posing now. The other thing that we don't know anything about yet.
Causing energy, because here everything is about energy. So.
Everything's about energy. The other interesting thing about this is, so why do people care about irregular structures? There's beautiful work going on in Jan Vermandt's lab, where what he's doing is he's taking ellipsoidal microparticles. And they can make percolating structures at interfaces, in particular when they have charge. Remember when they were coming end to end? They make percolating structures on an interface at coverages far lower than spherical particles would. And so those become highly elastic damping layers at coverages much lower than spherical particles would. So if you go back to a Pickering emulsion concept, where you want to, for example, make an elastic layer, but maybe you want to have an open structure where things can come and go between the two phases while still keeping it a stable phase. So we don't know where they're going to be useful yet. We don't know. To Mike's in charge.
If you had, so just to make sure I understand this, if you had two particles and you were somehow able to like pin the centers of them and turn one of them, would the other one turn as well?
We should be able to do this with the magnets and the laser tweezer, and the answer should be yes.
And then if you could make like a lattice and turn one, then all of them would turn?
If they were not in some configuration where they're so close that they don't have the room to redo the orientations. And so one can imagine right now that if we have this one in a laser tweezer, for example, just to be able to have it at some location, and only pinning, say, its center, put it in, so leave it free to rotate. Rotate this one with a magnet or another laser tweezer, would they co-rotate? The answer should be yes. It should also be very interesting because if we were to do, say, from end to end, to side, you'd have to put in a lot of energy to do this one, and at some certain energy, you would go into the metastable state as a snapping. So you should be able to interrogate that entire landscape.
Have you tried to work with 3 arms particles to make 2D networks?
We have them. We have triskelions, and we're just playing with them now. So you can make them out of metal, lithographically very nicely. And then, so, do you remember the Pringles potato chips example, the planar things that when they release them, they bend? If you do that with tri-arms, they bend. And you can make little open structures. Those are particularly interesting because, at least until they're assembled, they can't make a quadrupole. We've given something a symmetry that excludes the quadrupolar distortion. And so, they'll come together, but eventually in their assemblies can be together and come together by this.
So there's a question in cell biology, it's always a big open question, where you have the cell membrane and you have receptors on the cell membrane. And you would think intuitively that they're all homogeneously distributed. But for some reason there's some reclustering of these receptors. So I was wondering, because you have the surfactant you could call lipids in the membrane, and then you have the proteins which are different size. So I was wondering actually if, having these deformations, if actually with a certain density of these surfactants, you actually can cause this reclustering.
So
I was just
no,
wondering.
this is a very good question. So there's a literature that's just developing now called membrane curvature sensing and generation. There's work going in it, where the thought process is that a protein or receptor embedded in a bilayer is creating a distortion, which is storing energy owing to bending energies, that bilayers are typically thought to resist bending, and that those bending energies are causing this one's distortion to interact with this one's distortion, and causing them to come together. There's very early work showing that there are preferred orientations, and that these energies can interact over long distances. There's also open questions. For example, ellipsoidal particles for bending energy are predicted to come end to end. Now, I think that they orient end to end and repel. We know for surface tension, an ellipsoid wants to come side to side and attract. So while typically surface tension is neglected in these systems, one question could be, if we ever have a strained bilayer, for example, while there's a bending event or a necking event, could there be some competition between them? So all of you are anticipating things that I think we'll be spending the next 5 years on.
In the movie, I saw that you had single sitting in a single corner. How do the chains have these?
So we're just moving toward the chain step. And so one question is, the dense assemblies, do they have some sort of order parameter? And can we, if we make them smaller in scale, make them into things that have interesting mechanics? For example, with the surface pressure, what happens if we put enough energy to cause one to pop out of the interface and reorient, etc.? Looking at the chains, a very interesting question for the chains is going to be this yielding, the stiffness, and what does that mean in terms of, if we now look at each chain as having those joints that are characterized by this energy landscape, what does it imply for the dynamics of the entire chain? But open, early days. Early days.
Maybe a related question is, say you have a lot of detail about how two particles interact, but then when you're actually assembling things, you think about maybe thousands or millions of particles.
These are really good questions because we've worked on pair interactions. And one question is, are there multi-body interactions? If you looked at 1 and 2, can 1, 2, and 3 do something different? And
Well, how does a whole field of them?
how does a whole field behave? And how do you handle the fact that we have serious steric constraints in the systems? So that there's going to be a lot of memory. However, they arrived at a surface. If we throw them on pell-mell and they've made some sort of messy open chain and they're kinetically trapped, they can't anneal into something else. They become not kinetically trapped. What do they come to? All of the questions. Okay, I think he's going to come here.
So there's some wood theoretical work on membranes and balls on membranes with a density field and a height field. So the rules are, if it sees a negative curvature, it goes down the gradient, and if there are more particles there, it creates a deeper hole or a shallower hole, depending on your rule. So I was wondering if the ordered structures can be thought of as something like that with another extra parameter which gives you the direction.
Okay, so everything you talked about say, thinking about particles on a surface as being heavy particles that are beams that roll downhill, for example, those were the early work by Nicholson and Chan and the Cheerios effect. All of those are weight-driven things falling into energy webs owing to potential energy gradients. And that can sort out those ideas. Everything we're talking about, the idea is that that well doesn't exist, and so what we have instead is a coupling in, we don't have weight to play on that. So what we do instead is we have our saddles play with each other. And so this is a similar idea that's starting to develop in the membrane curvature sensing generation literature, which is that the distortions orient so as to minimize the distortion cost in some way. And for us, the leading order distortion is the quadrupole. And so the quadrupole moment tensor can couple into the curvature tensor.
Right, but this can be added into this with a directed field. We just added directed
That's
field.
right. Well, we could superpose these interactions, for example, if our quadrupole was large enough to fight with gravity and really heavy particles. So for example, I didn't weigh the bunk, but it was making a rather big quadrupole and riding up that distance. So I think it depends upon the scale. But yes, one could think about superposing these things, absolutely.
So I'd like to propose that we talk. Also, before the break, there's a hiking. Very important.
So about